That adds up to an odd, so I put another minus in front, change its sign. Mentally, I'm going to wipe out the row and column. That's going to leave me with 0, -2, 3, and a 5. I move down to 4. It's in position 2, 2. Keep its sign. Plus 4. Wipe out its row and column. I have the 4 corners left. And then -1. That's in 3rd row, 2nd column, so I need to change its sign from a -1 to a +1. And then 3, 0, 1, -2.
You're missing your 1.
Which one? Well, 1 times it. Yeah.
Right.
So 1 times it is just. Okay? So this is 2 times, so 0 minus a -6 is +6. Plus 4 times, so 15 minus 3 is 12. Minus 6. So this is 6 plus 48, which is 54, which, voila, is the same exact number as I got over here.
The last one,
Mm-hmm.
is that not 2? 4 -2, so it's +2?
Let me see, I wiped out this and this, so 3, 1, 0, -2.
So 3, are we multiplying the inside?
I'm cross multiplying, I go this way minus that one. Yeah, it's okay. It's hard, I mean, you guys are copying and listening.
Well, it's funny because what I did was add them,
Yeah,
and it worked out the same for
These-
the
these
first 2,
are-
but not for the last one.
these are a pain in the neck. Rule number 1 is if you have to do this by hand, you would not pick this row or this column. You would pick either the first row or the first column or the middle row because it's got a 0 in it. It's going to wipe out one of the terms. The more zeros, the better. Now, I'm not going to do this, but, I mean, don't copy this. I'm just going to throw down a few numbers. If I had a 4 by 4, I would pick a row or column to expand upon. And when I did that and I wiped out my rows and columns, I would have a bunch of 3 by 3s. Each 3 by 3 would then have to be done just like I did this. This is a royal pain in the neck. Computers don't like this so much either. I mean, they don't care about 4 by 4s and 5 by 5s. Your calculator will do it. I can't remember on an 84 how far up it'll go in dimensions. But there are determinants that need to be solved that are huge. And this takes a tremendous amount of memory, a lot of space. These can be a real problem. We only need it for the 3 by 3. But you'll talk about some of the tricks to getting these more manageable to compute. In fact, if I had a matrix like the following and wanted to determine it or to take its determinant, that's what's called a upper triangular matrix. And its determinant is 3 times 2 times 6. You can check it. You know, there's all kinds of tricks. The other totally weird thing is you can switch rows. That'll change the value of determinant by a -1. It'll change its sign. If you swap rows a second time, there will be no net change. Same deal with swapping columns. You swap 2 columns, the value of the determinant will change, but only in its sign. Swap 1 row followed by swapping a column, there will be no net change in the value. Now, I'll point that out as we look at some applications with cross product. So that's just kind of a general introduction to computing determinants. We only need the 3x3 case, and as obnoxious as it seems here, it will not be obnoxious when we use it because we will not have all numbers as entries. So, cross products. Back to vector world here. From dot products, I have the following. I have A dotted with B to be magnitude of A, magnitude of B, cosine of the angle between them when A and B are tail to tail. This allows me to solve for theta. It tells me when vectors are perpendicular, orthogonal, or not. It tells me information about that. I would like to do the following. I'm going to be working now exclusively in 3 dimensions. If I give you 2 vectors in 3 dimensions that are not parallel, they span a plane. The word span is a technical word. You'll see it defined in a linear algebra class. Basically, what this means is, I don't want to say they're inside of a plane because you could move vectors around as long as you don't change magnitude direction. They're the same vector. But if you picture a vector like this and this, there's a plane that holds it. Okay? I would like to find a third vector that is, they're going to use the word normal, but at the moment, before we start getting into weird language, I'm just going to keep using perpendicular because that's going to make the most sense at the moment. I'd like to find a third vector that's perpendicular to that plane. Or worded another way, well, let me write that down. So, find a third vector, and I'm going to put perpendicular in quotes because it's not the proper word. And I'm fudging. This is not quite kosher language because again, my vectors are not nailed down in place. I can move them as long as I don't change orientation or length, they're the same vector. So I can't really identify them just by themselves with a single plane. But you get the idea here. Worded much more precisely, if I'm given two vectors, non-parallel, find a third orthogonal to both of them. Okay? Now, we know what orthogonal means. It means 90 degrees, and in terms of dot products, it means 0. So I'm not going to do this, but I'm going to begin it. If, for instance, A was 1, 2, 3, and B was -2, 3, 1, I would be looking for a third vector, C, which I can call x, y, z, so that A dot C is 0 and B dot C is 0. That's what I'm looking for. So let me rephrase that. This would be A dot C would be x plus 2y plus 3z is 0. And B dot C would be minus 2x plus 3y plus z is equal to 0. So this is what I want to solve. And that'll give me a vector that does that. I mean, I'm looking for something that's orthogonal to both of these. So therefore, the dot product's got to be 0. Well, this is 2 equations, 3 unknowns. How many solutions? Infinitely many solutions. Infinitely many. Well, I mean, that makes sense. If I had a vector like this and a vector like this, I can do this vector, I can stretch it, shrink it, take it in the negative direction. I mean, there's infinitely many possibilities. So, I'm going to narrow it down. What I'm going to do, so infinitely many answers here. So since I have my pick, find me a particular one. And I want it to have magnitude of A, magnitude of B, and up above we had the cosine. I'm going to throw in sine here. There's nice applications of things that will have this magnitude. Torque, I think, if you're looking at a wrench going around a volt or something, the torque is given by this, where I believe one of these vectors is the length of the wrench and the other is the magnitude of the force you're applying to it. So this is a nice thing to have. I have infinitely many, so I can set the magnitude to be anything I want. And what that's going to do is nail it down. The only problem is you don't particularly care to solve linear equations and then get infinitely many answers and narrow this down. But that's what we want. Okay? Well, that's what the cross product does. So A crossed with B, it's got that X there. A cross B is the vector orthogonal to both A and B with magnitude of A, magnitude of B, times sine of theta, where again, you've got to have your vectors tail to tail. How to compute this guy? So here are two vectors. If I want to compute their cross product, A cross B, this is what I do. Across the top row, I'm going to put the vectors I, J, and K. In order, I'm going to put the vector A, and then the vector B. That determinant will give me this vector. Now, what I'm not going to do is work through all the drivel that you have to do to show that, in fact, this satisfies the conditions I want. But that's what they do. I mean, it's messy.
So we find the determinant, it's going to give us this.
It's going to give you a vector. It will be orthogonal to both of these. And it will have this magnitude. I'm not explaining why this solves that problem.
But well, I guess what I'm asking is, at the end of the last determinant that we did, the last two, we just came up with a number.
Yeah.
So
this is a mnemonic. I can give you a formula for this vector. But if we do this, it'll give me the vector without having to memorize. Okay, where do they do it in here?
I guess does that equal the magnitude?
No, I'm going to show you. It's going to give me a vector. Sometimes books will literally write it out. A1 times A2 times, and it's a messy, horrible formula. This is just a quickie way. Notice I'm not doing this abstractly. I've got specific vectors. So I, J, and K, I is your 1, 0, 0. J is your 0, 1, 0, and K is 0, 0, 1. You can either write this out using I, J, and K, or you can use this notation and stick your numbers in. So you can either do this, this, and I have to be careful with the pluses and minuses down here. So I'm always going to go across the top row. That's going to make my signs all go plus, minus, plus. So ahead of time I can either, if I'm going to do it with the I's and the J's and the K's, I can do this. If I'm going to do it in this notation, maybe I put a minus in to remind me. I start with I, wipe out its row and column. I have -4 minus a -4. That would be 0. I move to J. I wipe out its row and column. I have 12 minus 6. That's 6, but it goes in as a -6 or a -6. Because, yeah, say, shortcut? Yeah. I mean, I'm doing it this way because everybody's got to do linear algebra. If you know the engineering shortcut, just, feel free. It's just when you take linear algebra, you'll have to get a little bit more. But K, I wipe out its row and column. I have -6 minus a -3. So that's -3. And there's my vector. Now, you can check. This isn't so easy to check. But look, if you take 0, -6, and -3, and you dot it with this, you will get 6 minus 6. It's orthogonal. And if you dot it down here, you will get 12 minus 12. It's orthogonal. I'm not checking its magnitude, but this would be its magnitude. Of course, I don't know what theta is, and that's why I don't particularly feel like finding theta and then checking. But you guys get the idea here. Okay? Now, a couple things. One of the properties of determinants that I indicated was if you swap rows or columns, it will change the value of the determinant, but only by a negative. This is A cross B. If you look at B cross A, so I, J, K, it's going to be this. And if you compute this out, you will end up with this, the negative of this. This is not commutative. Order matters.
One more time, how did you get the 0, -6, and -3?
Wipe out the row and column for the I, and then compute the determinant of the remaining 2 by 2.
You mean, so that's -1 times
4.
Minus or plus?
Minus 1 times 4 minus a -4.
Okay, so
Yeah, so it becomes -4 plus 4. And if you make a mistake calculating, this gives you a quick check. Now, there's one other thing I've got to factor into this, but at the moment I just want to comment here. Questions?
It's okay if we don't do it that way, right?
Yeah, it's fine. I mean, I'm showing you in general. That's the way you'll see it in a linear algebra. If you know the shortcut or get somebody to show it to you, it goes quick. I mean, this doesn't exactly go long. I don't know that either method is really, with cross products, that different. I mean, it's just, well, anyways, it pops out. okay? If I swap a row, it changes the sign of the determinant. One thing to observe is that A crossed with B is not B crossed with A, it's the negative of B crossed with B. The magnitude of A cross B is magnitude of A, magnitude of B, times sine of the angle between these when I put A and B tail to tail. When is sine of theta equal to 0?
Two pi and pi, 0, pi, 2 pi. So
Okay. And our angles here are always between 0 and pi, or 0 and 0 degrees and 180 degrees. That's what makes sine of 0, 0. Which would mean what about my two vectors, A and B? The angle between them is 0 or 180 degrees. Those two vectors are parallel. And if the two vectors are parallel, sine is 0, and the magnitude of A cross B is 0, therefore, A cross B is the 0 vector. A cross B equals the 0 vector when A is a multiple of B, or when A is parallel to B. Be careful, I'm not saying this. And this is one of my quirky things. I'm really careful about notation. A cross B is a vector. A dotted with B is a scalar. So I can talk about A dotted B equaling 0, the number, but A cross B is 0, the vector. A is a multiple of B, the cross product is the 0 vector. One of the things, if you haven't taken linear algebra, one of the things you will learn about determinants is that if any row is a multiple of any other row, or if any column is a multiple of any other column, the determinant will work out to be 0. It's in fact a little bit more extensive than that. I can make a stronger statement, but not needed here. So you've got these geometric properties that are picked up from the algebra. And the algebra is reflective of those geometric properties. Okay, now, if I said, here's a plane, it's parallel to two vectors that are not parallel to each other. Find me the vector of exactly this length that's orthogonal to both of them. One of those vectors would be this, but the other would be its negative. You guys see? So the question becomes, which vector do we get? so the direction of A cross B follows the right-hand rule. Which is the site of one of my more stellar moments in high school, which, taking a physics test, doing a bunch of stuff with cross products and directions, and you use the right-hand rule, but I'm right-handed, so of course I'm writing with my right hand, and I never quite made the association that it mattered. And so all throughout this entire test, I used my left hand because my right hand was otherwise engaged, and got everything wrong. You know. So let me show you guys the right hand rule. And again, this is nothing I can possibly write down. All I can do is show. If I look at this vector A, and I look at this vector B, I've put them I put them tail to tail. I'm going to look at, let me pull this thing down. I'm going to look at A cross B. So with your right hand, I'm going to line my hand up with my fingers pointing in the direction of A. I can do that in one of two ways. I can do it this way or this way. If I do it this way, my fingers curl through the smaller of those two angles. If I do it this way, my fingers curl this way. What I want to do is to line my hand up along A so that my fingers curl through the smaller of the two angles. And if I do that, I do this, okay? Your thumb points in the direction of A cross B. So for these two vectors, A cross B points into the board. There is an orientation here. So again, if I put my fingers like this, they will curl through the smaller of the two angles. My thumb's pointing in the board. That's the direction A cross B points in.
I can see what you mean about the left hand, right hand.
Yeah, it's exactly the opposite. Yeah, I was a great physics student. If I look at B cross A, I've already told you the relationship between A cross B and B cross A is that they are negatives of each other. Well, if I line my fingers up along B, I could line them up this way, or I could line them up that way. If I line them up this way, then my fingers are curling through the bigger angle, so I don't want that. So instead I line B up, or my fingers along B in this way, rotate my fingers this way, points out of the board exactly in the opposite direction as up here. Negatives of each other. Okay? Okay, so so I guess these become the key points here. A cross B is the negative of B cross A. This is its magnitude. A cross B is a vector, not a scalar. It's got this magnitude. If my two vectors are parallel, their cross product is 0. If two vectors are orthogonal, their dot product is 0. But those are different zeros. Dot product 0 is a number, cross product 0 is a vector.
Can you say that one more time?
If I say A dot B is 0, that 0 is a scalar, a number. But if I said A cross B is 0, that has got to be a vector. Now, what I'm talking about here is just language, spoken. What I'm, in a practical sense, saying is, don't write A cross B equals 0, because that will never be the case. That's a number. Cross products are vectors. Okay? So, number, vector can't be equal. And I'm just taking the care because down the road it's very easy to get mixed up as to what you're dealing with here. All right. Now, you get these nice geometry things. I don't do planes till the next page. You get some nice geometry formulas. Do I want to mess with those now? Don't think so. There are some geometry formulas in section 12.4. As we need them, they'll crop up. So, at the moment, well, okay. Let's talk about planes and get a little bit of a start into it. Algebraically, let me see how I want to say this. Equations of planes look like the following. Okay. In particular, they're linear in all three variables. Out of context, I have no way of knowing if that is representing the equation of a line or the equation of a plane. There's no context here. But if I told you I was working in 3 dimensions, Z here could be anything. And that's the equation of a plane. And again, I can't tell you if that's referring to a number on the number line, the equation of a vertical line, or the equation of a plane. But by context, if I tell you it's the equation of a plane, we're working in 3 dimensions, it's clear. Each one of these 3 equations and all equations of planes are linear in all 3 variables. Linear meaning exponent is 1 on each of the variables. Okay? This means don't give me equations of a plane that look like this.
Does that third one, x equals 3, that one, does that like uniquely identify a plane? Or
Say again?
Does that uniquely identify?
Yes, that is the plane that every point on that plane has got an x coordinate of 3. And so if I have a three-dimensional coordinate system, I'm going to be 3 units out along in the I'm not the best at drawing in 3 dimensions, but if this is x, I would be looking at the plane that is 3 units. Let me see. Okay, the plane is parallel to the YZ plane. 3 units out along the x-axis. Do you see what I'm saying?
But I mean, does it have to be parallel though? Because in this case, it kind of.
Oh, it is. It's parallel to the YZ plane.
Oh, okay. Just because.
Because all I'm
X-
specifying is x is 3.
Okay.
That's all I'm specifying. So points on that plane might look like this. They might look like this. They might look like this. They all have an x-coordinate of 3, so they're 3 units out. If you measure the distance between any point in this plane and the YZ plane, it's going to be 3 units. Okay? Questions, comments? Okay? And we will talk about these graphs in another section or two. But this is not so far-fetched, giving answers like this, and when the time comes, I will warn you then as well. And, well, I'll show you then when this becomes a problem. But equations of planes, linear in all 3 variables. Okay? Now, in general, I can write the equation of a plane like this. And I can give you 3 points. 3 points determine a plane, and then you end up with a nice linear system of equations, and you solve to get those coefficients. That's all well and good. It's an algebraic way of doing it. But we're going to write down equations of planes using vectors. So to begin with, if I have a plane and I have a vector, I'll call that vector n, and I'll say that n, that vector, is normal to the plane P if given any 2 points A and B in the plane and dotted with the vector AB is 0. Again, 90 degrees. So you've got this language